All right, welcome back to Calculus 1. This will be the second lecture of the course, and in this lecture we're going to discuss limits. This is going to be an introduction to limits. So we'll call this 1.2, Introduction to Limits. Okay, and so we're going to take kind of a leisurely approach to limits. We're going to try to motivate them graphically, and then towards the end of the lecture, we'll get more into the sort of nitty-gritty, more hardcore definition of what a limit is. But let's start with just kind of a nice motivating example here. Let's consider the function f of x equals x cubed minus 1 divided by x minus 1, and then of course we should note here that this is not defined at the value of x equals 1. So this is only defined where x is not equal to 1. Otherwise, yeah, this is the domain on f here would be all real numbers except for the value of 1. Okay, so let's take a look at what this would look like visually here. And so I'm just going to draw a little xy coordinate plane here, and let's put in some values. And so this would be like 1, 2, 3, and so on, right up the y-axis, and then we'll put some values over here as well. This would be like 1, 2 on the x-axis, and then of course -1 over here. And so this isn't going to be like a precise visualization of this, but it looks something like this. It kind of comes up like this, and then of course at x equals 1 we've got a bit of a hole, and it kind of looks like this. Okay, so the function, so let's put on some labels here. There's y and there's x. So the function here kind of looks a bit like a parabola. The key piece of information that we need to notice here is that at x equals 1 there is a hole in the function, and that's due to this to the fact that you can't have a 1 as x, because then the denominator would be equal to 0 and you can't divide by 0. So when it comes to algebra, what we would basically be able to say about this function is that, yeah, there's a hole at 1 at x equals 1. Now when we get into calculus, and specifically limits, what we're going to be able to do, what we want to be able to talk about is, we want to be able to consider the value of f near x equals 1, right? And so this word near is very important, right? So it's important to kind of have a conception in your mind about sort of what a hole in a graph really looks like. You have to really be able to think about, right? So I've just got whole numbers written on here, right? Like integer values. But at every point between 1 and 0, there's infinitely many points between 1 and 0, right? At every one of those points, this function is defined. And then also at every point between 1 and 2, there's infinitely many points. At all of those infinitely many points, the function is defined there as well. It's just really at this one point, x equals 1, where the function can't be evaluated, it's undefined. Okay, so we can talk about getting infinitely close, and this is loose language here, infinitely close to x equals 1, or a better term probably would be arbitrarily close to x equals 1. So an example of a number that's very, very close to x equals 1 would be something like this. X equals 0.999, right? So this is it's a number that's very, very close to 1, but it is not precisely 1, right? The function is defined at this value, right? If I plug this value into this function up here, I have no problems, right? It's only when we get to the exact value x equals 1 where I have a problem. Okay, so it's very important to kind of get your head around that idea when it comes to limits. The idea of being extremely close to a point, but not precisely on that point. Okay, so let's take a look at what happens when we get very close to the value of x equals 1. So I'm going to just put some values on here, some example values. So we'll say, what about 0.75? Not exactly what you would call very close, but you know, close-ish. Well, let's move a little closer to 0.9. Then let's move a little closer to 0.99, 0.999, right? And then let's say 1's in the middle. And then on the other side, you know, maybe we'd say 1.001, that's equal distance on the opposite side. And then maybe 1.01, and then maybe, you know, 1.1, and then up to 1.25. Okay. So as you can see, this would be like we'd start sort of off, you know, over in this area somewhere, and then we would progressively move closer to the value of 1 until we're very, very close to it, right on top of it almost. And then on the other side, you know, you've got something like this, and then you get very significantly closer. Now, at each of those values, you can see what happens with the function, right? First it's there, then it moves over to here, then it moves over to there, gets progressively closer to the hole in the function. And the same thing on the other side, right? It starts out there, and then it gets closer, and then it gets even closer, and then it's, you know, right up on top of that hole. So the question is, what happens to the values as we get closer and closer to 1, but we're not equal to 1? So you can just pull out a calculator to confirm this, but I did this ahead of time. Plugging in some of these values, we get when x is equal to 0.75, then f of x is equal to 2.31. When x is equal to 0.9, then f of x is equal to 2.71. Right, and at 0.99, the value becomes 2.97, and at 0.999, it becomes 2.997, right? So getting very, very close to 3, as you can see, kind of these numbers sort of like converging to the value of 3, it looks like. On the other side, right, we would start above 3, 3.81, and then when x is 1.1, the value is 3.31, and then 3.03, and then at x equals 1.001, the value is 3.003. Right? You can imagine if we keep adding zeros in here and getting closer and closer to 1, then what we would expect is that this value would get closer and closer to 3. And similarly, if we keep adding precision to this point, you know, adding another 9 behind that, we might expect this value to get ever closer to 3 as well. Right? So while the function isn't defined at 1, there is such a thing as a limit to this function. And what we would say is that the limit of f of x equals x cubed minus 1 over x minus 1, the limit of that function as x approaches 1 is 3. Okay, and you can kind of see that here, right? Hopefully you can see it in this sort of numerical example. As we get closer and closer to the value of 1, the value of the function gets closer and closer to 3. Both as you move from below the value, it gets closer and closer to 3. And as you move closer and closer to 1 from above the value, it gets closer and closer to 3 as well. And so that's sort of the informal, well, that's the kind of intuitive idea of what a limit is, right? So a limit is, the idea of a limit is that as you approach this particular value of x, then the function is going to approach a particular value of f of x. And so here's a little more precise definition. This wouldn't be the most precise definition we'll see today, but this would be kind of an informal description. All right, we might say if the function, well, here's the notation. Let me start with the notation. The limit as x approaches c of a function f of x is equal to L. Okay, that's sort of the notation. Now, if I were to take our specific example from up above here and plug it into this notation, what we would have is the limit as x approaches 1 of x cubed minus 1 over x minus 1 is 3. And so that's the nice, this would be kind of the notation of limits. And let's talk through what this means. So if the function f, okay, if the function f becomes arbitrarily close arbitrarily close. Let me make sure we're focused here. Okay. If the function f becomes arbitrarily close to a point L, as x approaches c, from either side, then we say that L is the limit of the function at c. So if a function f becomes arbitrarily close to a point L as x approaches c from either side, the limit of f of x is L. Well, so then the limit as x approaches c of f of x is equal to L. Right. So that's kind of the informal description of what we mean by a limit. Okay. So let's do some more examples to kind of help motivate this concept, because it's a new concept. You haven't taken calculus before. You have not seen this before. This is new. This is a Calculus 1 brand new idea. And so here's an example. Let's consider this function, kind of a simple function on the face of it, but it works perfectly for illustrating a particular feature of limits. So the value of f is either 1 or 0, and it's 1 whenever x is not equal to 2, and it's 0 whenever x is equal to 2. Okay, so what does this function look like? Let's draw this. Okay, so we've got our xy coordinate system, and starting with, maybe we'll start with the bottom here at x equals 2. So let's put in some values here. So that's 1, 2, 3, 4. Okay, and then we'll say this is 1 and this is 2. So whenever x is equal to 2, the value of the function is 0. Okay, and just at that one point, that means, and then the rest, the upper piece of it, is everything else. So whenever x is not equal to 2, the value of the function is 1. So the function looks like this. Okay, of course, it goes into the negative x direction. Okay, looks like that. All right, so it's basically a horizontal line, and it's equal to 1 everywhere except at this one single point, x equals 2. And at that point, when x is equal to 2, the value of the function shifts down to 0. Okay. So it's something important to notice is that, so in the previous example, we had a hole at 1, and the value of the function was in fact undefined at that hole, and it namely because of the denominator would be equal to 0 if we were to evaluate the function at that x value of 1. In this case, f of 2 is defined, right? We can say clearly that f of 2 is equal to what? It's equal to 0, right? But the question is then, what is the limit as x approaches to of f of x. Okay, so let's in this, let's just look at the graph and make sure that we can see what that value is. So let's imagine ourselves on the x-axis moving towards the value of x equals 2 and getting ever closer to it. Right now, clearly, if we're on the x-axis moving towards the value of 2, then the value of the function is up here, and it's moving along the graph here towards the value of f of x equals 1. Right, the function value would be 1 as we get closer and closer. And you can see that as we get arbitrarily close to 2, the value of the function remains 1. Right, it's only at the exact value of 2 that it drops down. Everything up to it is equal to 1. Now similarly, let's imagine ourselves on the x-axis traveling in the negative direction. So as we pass 4 and we pass 3 and then we pass 2.5 and 2 2.25 and blah 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 and get very, very close to the value of 2. What's happening on the function? Well, similarly, we're traveling along this value of f of x equals 1. So from both directions, as we get arbitrarily close to the value of x equals 2, then the function value remains 1. Right, and so that's let's remember what the definition of the limit was that we just saw. We said that if the function becomes arbitrarily close to a point as x approaches a value from either side, then the limit of the function is the point. Right, so we can clearly see that the value of the function gets arbitrarily close to the value of 1 as the value of the function, the value that you're plugging into the function here gets arbitrarily close to 2. Right? Actually, it doesn't get close to 1. It is 1. It remains 1 everywhere except at the point x equals 2. And so for this reason, what we would say is that the limit as x approaches 2 of f of x is equal to, what is it equal to? It's equal to 1. Okay, so very important to notice here that f of 2 does not equal the limit as x approaches 2 of the function. Right, and that's an important thing to notice. Naively, one might assume that this is, this whole limit concept is just a stand-in or just a unnecessary complication, and it's really just evaluate the function at the point. Well, as you can see in this case, that's not exactly the case, right? In a lot of cases, it does just boil down to evaluating the function, but in general, it does not, right? So as you can see here, okay, so very good. That's a good example for kind of describing situations where the limit does not equal the value of the function at the limit point. Okay. So the first example that we talked through was an example of finding a limit numerically, right? So back here, you could say we more or less figured out what the limit was by just plugging in a bunch of values and getting really close to the limit point here. The second example was we sort of identified the value of the limit by looking at the graph, right? So it's kind of the graphical approach. Now we can also find limits analytically, right? Like just kind of like doing algebra and kind of thinking through sort of the rules of algebra and calculus. But we'll probably pause on that until the next session. So in this lecture, we're really more focused on kind of developing the intuition. Okay, but it won't always be like draw a picture of the thing or plug in a bunch of values and get close to it. We will develop some machinery that's a little more efficient than that. So let's take a look at this example here. We want to find the limit as x approaches 0 of this function, absolute value of x divided by x. Okay, now clearly this is not defined at x equals 0. Okay. All right, so that should go without saying, right? But just to point that out. So we can't plug in an x equals 0 because that denominator would blow up, right? So let's first start by considering values of x that are greater than 0, strictly greater than 0. So let's take a look at like what we would have here. So for example, f of 1. Well, that's the absolute value of 1 divided by 1, so it's 1. What's f of 2? Well, that's the absolute value of 2 divided by 2, so it's 1, right? And so on. So we can see that for any time x is greater than 0, then the value of this right here is going to be just 1. It's basically the the absolute value divided by the number itself, which is, basically the same number whenever x is positive. So you get 1s. What about below 0? Values of x less than 0. Right, so there we'd say something like f of -1, for example. Well, that's the absolute value of -1 divided by -1. Now, what is that? Well, the absolute value of -1 is 1. Divide that by a negative value, and you get a -1. And similarly, for all other negative numbers, you would get a positive divided by a negative, same absolute value, so you get -1. Right, so this function kind of has a very sort of simple setup as well. Let's take a look at what it looks like. Okay, so let's put a couple values in. Here's 1 and 2. Here's -1, -2, and then basically we just need 1 and 2 on the y-axis. Right, so, but then 0 is undefined, right? But everything above 0 is equal to 1, so it kind of looks like this, doesn't it? You would have something similar to this for the positive integers, and then for the negative integers, it would look like this. Okay, so that's kind of what the function would look like. What can we say about the limit? Let's again kind of imagine our scenario where we're running along the x-axis. So if we're on the x-axis, moving towards 0 from the left-hand side, well, we would be down here, wouldn't we? We'd be running along along the value of the function, and we'd be heading towards the value of -1. Well, we'd be equal to the value of -1. We wouldn't actually be approaching. We'd be equal to it up to the value of x equals 0. And similarly here, as we approach x equals 0 on the x-axis, we would be up here, right? We'd be at the value of f of x equals 1, and we would be constant at that value, approaching -1, you might say. Or sorry, approaching 1. So what does this mean? So here the real interesting part about this example is that as we approach 0 from the left-hand side and from the right-hand side, we actually approach different values on the function, right? So from the left, so meaning from this direction, f of x goes to -1 as x goes to 0, right, from the left. But from the right, f of x, right, up here, f of x approaches 1 as x approaches 0. Okay, so, and when I say approaches -1 and approaches 1, well, it's equal to 1 and -1 in both cases, right? So that's kind of some weird terminology, but basically the issue here arises in the fact that the function is approaching / equal to different values as we approach x from different sides. And so remember, our definition said that as x approaches c from either side, right? So as x approaches c from either side, then f needs to become arbitrarily close to a particular point L. And if that's the case, then you have a limit. This is not satisfied here, clearly, right? So in this example, we're approaching different values as we approach the limit point x equals 0 from different sides. So in this case, we would say that the limit as x approaches 0 of the absolute value of x over x does not exist, right? Precisely because the left-hand side and the right-hand side do not agree on what they are approaching, right? Now, in order for the limit to be there, you have to approach the same number. Okay, so does not exist. Very good. Examples are key when it comes to limits, I have found. So I'm going to do yet another example. It's important to develop intuition about this. It's been my experience in teaching calculus that frequently people get hung up. They want to be able to, plug and chug here with limits, and there's an intuition that needs to be developed with regard to limits that only examples can accomplish, right? So only doing examples, seeing lots of different functions and thinking it through a lot, can you get past this inclination to do plug and chug kind of mathematics. Because calculus is one of those subjects where you're not going to be able to just start plugging and chugging. You have to really kind of think things through, visualize a bit more than what you're probably used to in algebra. Okay, so here's another example. Consider the function f of x equals 1 over x squared. So then what do we want to know? Let's find the limit as x approaches 0 of this function. And of course, all other points on this function are uninteresting limit-wise. The limit at 0 is the interesting one, of course, because it's undefined there. So let's look at what does the function look like. Again, for this, I've kind of, looked at this ahead of time. You might have to spend a little more energy, like kind of drawing the functions, maybe pull out a graphing calculator, hop on Wolfram Alpha or something and visualize the thing first. But it kind of looks like this. It's, maybe you would have anticipated this, but the graph is asymptotic at x equals 0. Right, so here you've got 1 and 2, negative 1, negative 2, right, and then of course 1, 2, and so on. And then negative 1 down here, just to be thorough. So the graph kind of at x equals 0, because you're dividing by 0 or dividing by an extremely small number, the value of the function, 1 divided by an extremely small number is an extremely large number. So that's why the graph that's why the function kind of blows up at x equals 0. So we're interested in the limit here. So what happens when we approach x equals 0? Here's the limit point. What happens when we approach it from both sides? Right. Well, as we move closer and closer to 0 from the left-hand side and from the right-hand side, in this case, the function it heads off to positive infinity, doesn't it? The value of the function grows without bound as we get closer and closer. And so f of x goes to infinity as x goes to 0. Right? So the value of the function heads off to positive infinity. Now, that's true from both sides. Right? And so you might be tempted to say that the limit of this function is infinity. It's an infinite limit. So in this case, we'd actually, this is sort of a technicality, but we would say that the limit does not exist. Okay, we would say that the limit as x approaches 0 of 1 over x squared does not exist. Right? And specifically, we would say that, intuitively, we know that they both kind of head off to the same place. But technically speaking, this function does not approach a real number as x approaches 0. So we would say that the limit does not exist because f of x does not approach a real number as x approaches 0. All right, so infinity is a concept. Really, it's not a number. It's certainly not a real number. So by real number, of course, we mean the real number system, right? So the real number set. So the real number being like all of the numbers that are represented on the number line, both in the negative and positive direction. And so in this case, the function heads off to infinity, does not approach a real number. Okay, so the limit in this case does not exist. All right. The next example is the case where you have oscillation occurring. What does the limit look like in the case of oscillation? So this is a classic example, calculus, but the function is f of x equals sine of 1 over x. Right. So the argument here is 1 over x. Now, obviously not defined at x equals 0. Okay, but as we get arbitrarily close to 0, what happens? Okay, as we get arbitrarily close to the value of x equals 0, what happens to this function? Well, it's a sine function, right? And so, it's important to remember your trigonometry here. What we're doing is we're plugging in a real number into this function, and the value here is treated kind of like an angle. So you can plug in really large numbers, really small numbers, and you're going to get some kind of an angle or some kind of a real number output. But the value of the sine function is bounded above and below by 1. Okay, so put those on here. So this is positive 1, this is negative 1, right? And then out here you've just got all of the x values. And then out here you've got all of the negative x values. Right, and so the function, it's a normal sine function. It's just got a weird argument. So it's going to kind of come in, this is obviously kind of I'm riffing on the idea of the sine function, but what it's going to do is it's going to get very, very close to 0, and as it gets closer and closer to 0, the rate of the oscillation will increase really dramatically. And it does the same thing from the other side until right in the middle you're going to have oscillation. So like just the smallest digit change will flip the value of the function from -1 up to 1. So the oscillations become so as you get arbitrarily close to 0, the rate of oscillation becomes almost infinite, right? So it's so fast that it's flipping between 1 and -1 like instantly almost. So this one is a tricky one, and what I recommend is this is a great resource. I'm sure people who are online kind of know this, but plug this function into Wolfram Alpha and you'll get a nicer picture of it. Also, you could just Google it. And it's a classic function that's used to discuss limits, but my visualization skills being sort of limited to my handwriting, my drawing skills, this doesn't do it justice. But the idea is that you can imagine that as the oscillation rate increases, when you get arbitrarily close, infinitely close to this value of x, then the rate of oscillation is so rapid that it's as though the function almost exists in two places. Okay, so what we would say then in the case of this is that the limit as x approaches 0 of the sine of 1 over x does not exist. And that's because the function oscillates between two fixed values as x approaches c. Right. So the other thing to notice here is that even though the rate of oscillation increases infinitely, like it's infinitely fast, the range of the oscillation remains constant between -1 and 1. So you can imagine if those two concepts are juxtaposed, what really is taking place at x very near x equals 0 is pretty remarkable. So what ends up happening is that causes the function to oscillate between two fixed values, and consequently, from the left and the right, you get no agreement on this. So for that reason, we say that the function doesn't have a limit at x equals 0. Okay, very good, very good. So we've kind of covered a few things, but let's recap here. So common reasons for the non-existence of a limit. So what are those reasons? Well, the first one we saw was when f of x approaches different values from the right-hand side and from the left-hand side. So the right-hand side limit does not equal the left-hand side limit. Right, that was the first one. Right, so they basically don't agree when they come together. Right, so that was the first example that we saw. The second big reason is that the function could potentially increase without bound. So the function increases or decreases, of course, without bound. And that's just a fancy way of saying, look, the function heads off to infinity, or conversely negative infinity, right? And for that reason, we would say that the limit is not a real number, and technically you can't be a limit if you're not a real number. So so that's the other one. And then the third one that we just talked about is when the function oscillates between two fixed values. The fixed is important. There are examples where the oscillation occurs, but it's not between two fixed values, where you could have arbitrarily increasing oscillation. But if the values that you're oscillating between tend towards a third value, then you might have a limit that actually does exist. Okay, so for that reason, those are the main reasons why a limit might not exist. Okay. And I think that's kind of where we'll leave it example-wise. Now, with the last couple of minutes, I want to spend a little bit of time talking about a more formal definition of of what a limit is. So let's start with the definition, and then we'll work through an example. Now, this definition is the definition that would be typically used if you are trying to prove the value of a limit. Those proofs are while we'll talk about them a little bit in this class, they're not typically what you would expect to master in a Calculus 1 course. Calculus 1 is more about identifying the concept of a limit, being able to work with limits somewhat. You may be introduced to the idea of a proof in Calculus 1, but generally speaking, people who are taking Calculus 1 don't have sort of like the mathematical maturity to really like wield proofs comfortably. And it's really like, so for that reason, like most of the proof work in a calculus course is kind of put off until you get into a course called Real Analysis, which is another undergraduate course but it basically treats all of the calculus concepts with a lot of rigor and sort of proves a lot of the fundamental ideas of calculus. But we will discuss it here just kind of briefly, and then we probably won't bring it up again. But here's kind of the more formal definition of what a limit is. So let f be a function defined on an open interval containing c. So let f be a function, right, defined on an open interval containing c. Okay. Now, c is going to be the limit point, and so what's meant by this open interval, the importance of the open interval idea is just that there's room on both sides of c, right? We have to approach c, right? So the function has to be defined on some interval around c so that we can approach c and and evaluate c in the function at those values near it. So let f be a function defined on an open interval containing c. Let L be a real number So it's more like a comma here. Let L be a real number. Then the limit as x approaches c of f of x equals L means that, and this is where it's going to get a little like hairy, it means that for each epsilon greater than 0, there exists a delta greater than 0. Okay, such that if the distance from the limit point is less than delta, then the distance of the function from the limit is less than epsilon. Okay, so I don't expect that to make a lot of sense right now. Let's recap the definition, and then we'll draw some pictures and try to figure out what the heck this is about. So let f be a function defined on an open interval containing c, right? So f is the function, c is the limit point. That's the thing that we're traveling towards on the x-axis. And we need the open interval because we have to be able to approach c from both directions, right? Okay, so then let L be a real number, right? L is the real, it's got to be a real number, important. It's not in infinity or negative infinity concepts. But then when we say that the limit of f of x as x approaches c is L, what that means is that for any epsilon greater than 0, there's going to, so epsilon is just a Greek number. It's a Greek symbol that is a stand-in for a number, right? So any positive number, for any positive number, there exists another positive number, which we call delta, such that if, and let's look at this inequality here, x minus c absolute value less than delta greater than 0, all this means is that the distance between x and c is a positive value, it's greater than 0, but it's less than whatever delta is. Okay, so it's less than whatever delta is, right? So for each epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and c is less than delta, then the distance between the value of the function and L, the limit, is less than epsilon. Okay, so the way this usually works is that, and this is loose speaking, but somebody gives you an epsilon greater than 0, right? So someone hands you an epsilon greater than 0, says, all right, I want you to find a delta such that I'm within 0.000001 of the limit, right? And then if it's truly the limit, then you should be able to go out and find a delta. Somebody gives you an epsilon greater than 0, you find a delta greater than 0 such that, you know, this is true. F of x minus L is less than epsilon when 0 is less than x minus c less than delta, right? So that's the idea. Okay, I find it's instructive usually to draw a picture. So let me try to draw a good picture so we can look at this. Okay, so if this is your x-axis, and this is your f of x, your y-axis, and let's say the function kind of cruises in like this, and let's say that here's c, right? So we can naturally see that c corresponds to this value on the function, and so then this here would be, you know, f of c, but we're going to call it L, right, for this picture. So if somebody comes in and says, here's an epsilon greater than 0, a very small distance, I want you to be very, very close to L. I want you to find a value of x that when you plug it into that function, you're within this distance of the limit, right? And so when somebody gives you an epsilon, they're basically defining a range, L plus epsilon and L minus epsilon. Okay, and so you can see what that would do out here. Okay, so if somebody gives you an epsilon, and remember these epsilon, the idea behind the epsilon is that it's arbitrarily small, right? Like epsilon is 0.0000002. Right, very small numbers, and the fact that it's arbitrarily small means that it's basically infinite. You can think of it as basically being infinitely small. Okay, so if somebody gives you a range that they want the value of the function to be in, then you need to be able to go out, in order to prove it, you need to be able to go out and figure out what a delta would be, such that c minus delta and c plus delta would produce a value of f that's within epsilon of L. Okay. So that's the idea with the epsilon delta proof. Now, in practice, it's not always, as I say, it's not going to be the focus of this course, but I want to do one example just because some people who are watching this may find this useful. They may find it useful in terms of like developing intuition. They may also find it just kind of fascinating that, how the level of rigor that's involved here. So let's do a simple example. We want to use the epsilon delta definition to show that the limit as x approaches 2 of 3x minus 2 is 4. Okay, so a pretty simple function here. This is like a linear function. It's basically a line with the slope of 3, cuts through the value of negative 2 as a y-intercept, right? And so you can easily see that if I plug in 2 for x, 3 times 2 is 6, minus 2 is 4, so clearly that is the limit, right? This function is defined for all real numbers, so there's no holes or anything. So this is a very obvious example, but we want to use kind of the simple example to make sure that we can see the machinery of the proof of using the definition, right? So what we want to start with is we want to, always you want to assume that epsilon greater than 0 is given. And all that means is that, hey, somebody gave me an arbitrary epsilon and I have to work with it, right? And that epsilon can be, the fact that it's arbitrary means it can be as small as you like, which means it's basically, you can think of it as infinitely small. So that's always the first piece, right? So you always have to start from that assumption. That's the assumption that the argument is based upon. Now the thing you want to do really in the background of these things is to start by looking at this value here, right? So when you have a concrete function and you have a concrete value of L, you can start evaluating this. And so when I do this, you can see I get 3x minus 2, and then minus L would be minus 4, right? So it looks like that. And of course I can I can do some I can do some work here, and you can see that I get 3x minus 6, right? And then I can even do some factoring here inside, right? I get 3, and then it's what, x minus 2, like so. And sorry, these are equal. And then ultimately I can pull the 3 out because the absolute value of 3 is 3. So 3, and then it's just x minus 2. Okay, so there's some work that can be done with this piece here. Okay. Now, at this point, this will be kind of the leap for many people. But at this point, so I'm given an epsilon. All right, I've done some background work here. I've looked at this thing. And what I can say is, and this will be the piece that we'll talk through in a second. Why would you make this choice? But we can choose delta equal to epsilon over 3, right? Or 1/3 of epsilon. Now you may be saying, why in the world did you do that? Where did that come from? And we'll see in a second where that came from. But the idea here is someone gave me an arbitrarily small epsilon, and from that epsilon, I can derive an arbitrarily small delta, right? No matter how small epsilon is, I can always divide it by 3, right? That's just the property of the real numbers. You can always divide a real number by any other real number. Non-zero real number, right? So whatever epsilon happens to be, no matter how small it is, there's always going to be some delta that's equal to epsilon divided by 3. Now, the question of why we chose epsilon over 3 will come out in a second. But hopefully that property is clear, right? If somebody gives me some arbitrary epsilon and I set up something like this, no matter what the number epsilon is, I can always figure out a delta, okay, just by dividing it by 3. So then why did we do this? Well, remember up here in the definition, it says somebody gives you an epsilon, you find a delta such that you're within epsilon distance from L whenever you're within delta distance from C. So what we would do next is we would say, all right, let's assume that we are within delta distance of C, in this case 2, so x minus 2 is less than delta. Okay. So we're going to assume that. We're assuming we're going to plug in a value into our function that's very, very close to the value of 2, right? It's, you know, it's very, very close to the value of 2. It's less than delta away from 2, right? Remember the picture here. So we're somewhere in here. Right, we're going to plug in a value that's inside this interval. All right. So when we do that, what can we say about this piece here? Well, we can say the following. We say then that f of x minus L, you know, is equal to, well, we did all this math here, right? Well, it's equal to 3 times this. Okay, so it's equal to 3 times the absolute value of x minus 2. Well, what do we know about the absolute value of x minus 2? Well, we know that that is less than delta by assumption, right? We're assuming that we're going to plug in a value that's inside this interval. So that means the distance between x and c, in this case x and 2, is less than delta. So that means this whole thing here is less than delta. And what is delta? Well, we chose delta to be equal to epsilon over 3. Oh, sorry, that's 3 delta. Shoot. So this piece here is less than delta. So this whole thing is less than 3 times delta. Sorry. Key point there. Key point. Actually, let me just erase this and start that over. So if the distance between x and 2 is less than delta, then 3 times the absolute value of x minus 2 would have to be less than 3 times delta. Okay. And 3 times delta, well, we know what delta is, right? We chose it up here, so this would be equal to 3 times, and then delta we said would be whatever epsilon is divided by 3. Okay. And then, of course, 3 times epsilon over 3, well, that's just epsilon. Okay, so what have we shown? All right, well, what we've shown is that you gave me an arbitrary epsilon greater than 0. I used whatever that epsilon is. I set that my delta equal to 1/3 of it. Then I assume that I assume my value of x is between 0 and delta, within delta of the limit point 2. And then I can, obviously we can go through this exercise to see that f of x minus L is equal to 3 times the absolute value of x minus 2, which is less than 3 times delta, which we see is equal to 3 times the ratio of epsilon over 3, which is just epsilon. Okay, so basically what I've shown is that f of x minus L is less than epsilon whenever x minus 2 is less than delta absolute value. Okay, so that's the limit definition, right? So in doing this, you could say, okay, now I'm going to give you the smallest imaginable epsilon. Well, that means you're basically right up next to L. You're saying, I want a value of the function that is arbitrarily infinitely close to L. Can you go find an x that does that? Yes, I can. I can just take whatever you gave me as epsilon, I can divide it by 3, and bada bing, bada boom. I can plug that value in down here, and that will get me arbitrarily close to L. So that's the idea with the epsilon delta proof. Now, hopefully that came across, at least pieces of it. Again, this is not a proofs class. That's really more like a real analysis course. But I find it's useful to instructive to present some of that material to students and give them the option of thinking about it ahead of time, right? So, okay, so that is it for Lecture 2, Introduction to Limits. Next time we'll discuss evaluating limits, and we'll get into specifically evaluating them analytically. And we'll get into some of the niceties that exist for thinking about the values of limits. See you then.